Hello everyone, thank you for your interest in the presentation. My name is Rojin Darakhshande. I'm a PhD student at Mechanical Engineering Department, Purdue University, and today I'm going to present my work on ultrasound PIV uncertainty quantification. According to the topic, let's start with what is ultrasound image velocimetry or UIV and why we need to quantify the uncertainty in those measurements. UIV is an emerging method for non-invasive flow measurements. In UIV, opaque flow tracers are injected into a working fluid and intensified by a transducer. Then the received signals are digitized and processed further to form an image. After imaging, it's pretty much like PIV. The images are processed using PIV cross-correlation-based algorithms to measure the velocity field. UIV has two significant characteristics which brought a lot of attention to it in fluid mechanics community. First, high spatial and temporal resolution, which enables us to resolve complex flows in complex geometries. Second, it is able to resolve opaque medium, so it does not have a lot of optical limitations. Given these two advantages, the first application comes to mind are clinical ones. UIV could potentially be used for helping in clinical decision makings in very complex cardiovascular and cerebral flows. Obviously, this means understanding the measurement error sources is a must. Otherwise, the clinician cannot rely on the measurement to decide about his or her patient's life. Other than clinical applications, UIV can be used in experimental studies, where the optical method fails, like multiphase flows, and the measurements can be used for design purposes or as reliable validation datasets for numerical studies. Again, in this case, the uncertainty of measurements is a must. Therefore, measurements uncertainty is crucial in assessing the statistical significance of UIV error sources. But what is uncertainty? Uncertainty is an estimate of a bound within which the true measurement error is expected to lie with some confidence. However, quantifying it in UIV is non-trivial due to error sources specific to image formation, their combination, and propagation through measurement change. To explain these error sources, we need to know how images are formed. Here you can see in the left optical images versus ultrasound images. First, the particle's reflected pressure wave creates a non-Gaussian point spread function. Here you can see other than Gaussian, you have cosine modulation. Then it goes through Hilbert modulation, which consider for negative intensities due to cosine. And at the end, all these steps leads to a non-Gaussian point spread function, which is definitely an error source because all of the fittings and peak location estimators in cross-correlation algorithms are designed based on Gaussian point spread function. Also, particle images are formed across several ultrasound scales, yielding in elliptical particle image shape. Additionally, clusters of tracers produce a single bright image intensity and a speckled image pattern. At the end, compared to conventional PIV images, UPIV has significantly higher noise due to lack of filtration for reflection from the non-tracers obstacles. Even though ultrasound image formation is different than regular PIV, uncertainty quantification methods for PIV still can be applied to them, since both PIV and UIV go through the same processing procedure. So in this study, we reviewed the PIV methods to see which one adjusts more for our purposes. We can categorize them into two main groups, direct and indirect. Indirect method predicts the displacement uncertainty by calibrating the variation of uncertainty to various image parameters and signal-to-noise ratio metrics. But direct methods estimate the uncertainty directly based on image or correlation plane. Presently, 3 direct methods are available to estimate the displacement uncertainty: image matching or IM. In brief, in the IM method, the standard uncertainty is defined as the standard deviation of the disparity error. The disparity error relates to the residual mismatch between paired particle image position after a converged iterative deformation. In a perfect shift, disparity should be 0, so it's representative of the error. The performance of this method is sensitive to the accuracy of the particle position and deteriorates with seeding density, increasing seeding density, and noise. The second one is correlation statistics, or CS, which estimates the uncertainty again using the image disparity but at the pixel level. In a perfect shift, the correlation peak at the end of a converged window deformation procedure should be symmetry. CS relates the peak's asymmetry to the uncertainty and calculate this asymmetry through sum of a covariance region. Third is moment of correlation, or MC, which predicts the uncertainty by estimating the second order moment of the PDF of displacement contributing to the cross-correlation plane. For an ideal shift, the perfect cross-correlation can be represented as a convolution between Dirac function at the location of a shift and autocorrelation of particle image diameter. Any deviation is due to the error influencing the measurement. Hence, in MC, we will remove the particle image diameter information to get the phase-only correlation, which is directly related to PDF of all possible displacement, and obtain the uncertainty as a spread of its peak. In this work, we try to adjust the methodology of these three methods in order to increase their sensitivity to error sources specific to UIV. As mentioned, IM estimates the uncertainty using statistical analysis of the disparity. For obtaining the disparity, raw images going through iterative window deformation to obtain I1 bar and I2 bar, which are matched images. We will calculate the multiplication of intensity of two matched images to find local maxima, which are potential particle pair. The initial positions is used in 3-point Gaussian fit to find an exact position in each frame separately, and the difference is a disparity vector. You can see here the mismatch. Now the problem is, first, in UIV, point spread function is not Gaussian. And also in UIV, we have a stretched elliptical particles with aspect ratio 1:4, causing similar pixel intensities in the 3-point neighborhood of the center. Thus, a 3-point fit often fails or is inaccurate. At first, to overcome the problem, we decide to use other fitting methods like least square fit for calculating the disparity. However, it didn't improve the results. The reason is when we have high noise level in the image and the seeding density is also high, meaning we have particle overlaps, the fitting performance will get worse. Now, as the 3-point fit is just based on 3-point around the peak, will not be affected much with error sources, but other fittings like least square, which are dependent on a region around the peak, will be more affected. As the high seeding density and high noise level are common situation in U images, and also the particle shape is not Gaussian, this method is not recommended, and we expect worse result in higher aspect ratios. In CS, uncertainty is defined as cross-correlation peaks error, which obtained through the correlation peaks asymmetry, and this asymmetry is calculated through sum of a covariance region. In general, this sum is computed over a neighborhood region proportional to the particle image size in a circular region. For UIV measurements, the CS uncertainty calculation is modified to dynamically set the covariance sum region in each direction proportional to the estimated autocorrelation diameter. So at the end, we have elliptical covariance region. The performance of adjusted CS is assessed through artificial ultrasound images. The detail of processing will be explained in next slide. And as it has been established that the reliable uncertainty algorithm can predict uncertainties that their RMS matches with the RMS of error, here I put the RMS of error, new CS, and previous CS. In this plot, you can see the RMS versus the aspect ratio of the particle. The black line is the RMS of error. The red line is the RMS of CS, using circular covariance region, the conventional one, and the green one is the CS using elliptical covariance region. And you can see the result gets closer to the RMS of errors, and for aspect ratios 2:4, we have 65% improvement. In MC method, the standard uncertainty is defined as the standard deviation of the PDF. Why is that? For an ideal shift between the particle image patterns, the perfect cross-correlation peak is the convolution of a Dirac function representing the shift and the autocorrelation of the particle image. So in MC, we will remove the particle diameter information to get the PDF, and this PDF the spread of this PDF is our uncertainty. The standard algorithm assumes that the PDF is a Gaussian and convolved with another circular Gaussian kernel to broaden the peak region. This leads to more reliable PDF standard deviation estimation. The complete flowchart comes here, but because our improvement is in this part, estimation of a PDF spread from the kernel and the PDF itself, we were focused on this part. The formula to obtain a PDF minor and major axis simplifies to this when the Gaussian kernel is circular. Here, Px and Py are PDF's major and minor axis, Cx and Cy are convolved PDF peak diameter, and d bar is the circular Gaussian kernel diameter. The way it is calculated comes from the fact that if two Gaussian functions convolve, the covariance of the convolution will be the sum of covariances. Now, if one of the functions is circular, which is the case in conventional MC, the sum of covariance simplifies to sum of the variance terms. And the important part is the kernel diameter, or d bar, is dynamically estimated from the cross correlation peaks width, so the convolution result will be most representative of the standard cross correlation. In order to consider the particles stretch in ultrasound images, the convolution kernel is also defined as a non-circular Gaussian function, since in UIV measurement, the cross-correlation peak is not circular. Thus, the PDF diameter and orientation is calculated from these derived equations. Again, we have assessed the performance of adjusted CS with the artificial ultrasound images, and you can see 50 to 60% improvement for higher particle aspect ratios. To do performance assessment of original IM and improved MC and CS, we designed Monte Carlo analysis where we use synthetic dataset and various parameters that affect the error in UIV. In our study, we looked at the effect of particle image aspect ratio, noise, density, and displacement. The baseline parameters are kept constant and other parameters have varied in the image. You can see the parameters in the table, and here is the image, the artificial ultrasound images with baseline condition and two aspect ratios, the minimum aspect ratio of 1 and the highest aspect ratio of 4. So once we generated the synthetic ultrasound images, we performed PIV processing to report error in our measurement and compare that to the estimated uncertainties. We performed multi-grid deform approach with a standard cross-correlation and least square feet for the peak location. We used one pass with iteration and validation and another pass without them. The window size was 64 by 64 without overlap. For each case of Monte Carlo study, we have 45,000 measurements to make sure the error and uncertainties has converged. Here is the Monte Carlo results. You can see the RMS of errors and uncertainties versus aspect ratio of the particle, seeding density, displacement, additive noise, and multiplicative noise. The red lines are the MC results, improved MC results. The blue line are improved CS results. The green one is the IM results, and finally the black one is the error. The improved MC is the most sensitive method to all error sources, and its predictions are within 5% of the RMS of error. As expected, the IM performance get worse in higher aspect ratios, start from aspect ratio of 2, and as baseline aspect ratio is 3, you can see a bias error for IM in all other plots. Even though CS has been improved a lot, it still overpredicts the uncertainty, which should be more investigated. For the future works, we will find the sources of bias error in CS and also do the experimental validation of the methods. So the setup and the test cases are ready, and we just need to do the experiment. Here are the reference, and thank you for choosing this presentation, and I hope it will help you guys. If you have any questions, you can ask me in question and answer time blog, and you can also email me for further questions.